Hey everyone, this is our last video with matrices. Matrices day 3. We're talking about determinant applications. And the first one that comes to mind is Cramer's rule. Gabriel Cramer in the mid-1700s, 1704 to 1752. So before the founding of this country, this guy came up with this, which is, I think, pretty damned amazing, that you could, perceive this, even think about this. And he said, if I have a system of equations, and let's start with something gentle and easy, like 2x minus 3y equals negative 4, and 5x plus 7y equals 1. We know a bunch of ways of solving this system. We could use substitution, where we solve one of these equations for one of the variables and plug that into the other equation, and then solve for the variable there, and then plug that back into the first equation to get the ordered pair that represents the point of intersection. Most students at this point in math like using elimination. But if I do elimination here, I have to multiply this row by something and this row by a different something, and that's going to be icky. What I want to look at here is how can I use determinants to help me with this? Well, Cramer says that we can do this kind of thing. The notation that we see is the determinant of the x's over the coefficient matrix determinant. And so for us, what's that going to look like? Well, when we make the coefficient determinant, that's just the determinant made up of these four coefficients: 2, negative 3, 5, and 7. Okay, so that's the thing that goes on the bottom. 2, negative 3, 5, and 7. Now what goes on top is this x determinant thing, and he said what we need to do is we need to replace these x coefficients with the answers. And so we're going to have negative 4, 1, negative 3, 7. Right? So all we did was we took these two, we got rid of them, and we put the answers in their place. Okay. So the determinant on top, this times this, minus this times this, negative 28 minus a minus 3 is negative 25. And on the bottom, this times this, minus this times this, is going to be 29. And so what do we get? Well, look, there it is. There's our x value. That's nice. Look, I didn't have to do any fraction suffering. You know what I mean by fraction suffering? Here, let's go look at fraction suffering for a minute. Hey, let's solve this system with substitution. 2x equals 3y minus 4. X equals 3/2 y minus 2. And then I take this and I plug it in for the x in the other equation. 5 times 3/2 y minus 2 plus 7y equals 1. And so I get 15/2 y minus 10 plus 7y equals 1. Or 14/2 plus 15/2 is 29/2 minus 10 equals 1. 29, and this has a y next to it. 29/2 y equals 11. I multiply by 2. I get 29y equals 22, or y equals 22 over 29. But I haven't found x yet. I know that x equals 3/2 times y minus 2. So 3/2 times 22 over 29 minus 2. And so we get 33 over 29 minus 2 times 29 is 58 over 29. And so I get negative 25 over 29. Now, I know how to do it, but wow, dealing with all those fractions sucked. What was it that Cramer said? Cramer said, look, don't stress. All you have to do is do the x determinant. So we replace the x's with the answers over the coefficient determinant, 2, 5, negative 3, 7. So here we had negative 28 minus a minus 3. And here we have 14 minus a minus 15, which is 29. And that's what our x value is. And if we want to find y, well, the determinant on the bottom is the same. 2, negative 3, 5, 7. But on top, we're going to replace these y's with the answers. So 2, 5, negative 4, 1. And so now I already know the denominator is 29 because I did that over here. 2 minus a minus 20 is 22. Oh my God, Cramer's rule is so freaking fast. So I like Cramer's rule a lot for solving systems of equations. Why don't we show Algebra 1 kids and Algebra 2 kids about using Cramer's rule? Well, so you have to teach them matrices first, and then you have to teach them determinants. And so that's a whole bunch of stuff for little brains, and so we often choose to wait until you've developed a more mature understanding of mathematical things. But you're right, we could do this with Algebra 1 kids, and they might be thankful, but I know they wouldn't be as appreciative as you are to have it. All right, so can we solve a 3 by 3 using Cramer's rule? Well, so if I have this 3 by 3, x plus y plus z equals 6, 2x minus y plus z equals 3, 3x plus 0y minus z equals 0. How do we use Cramer's rule here? Well, Cramer's rule says if you're looking for x, then you do the x determinant over the coefficient determinant. The coefficient determinant is just the determinant with all these coefficients, 1, 1, 1, 2, negative 1, 1, 3, 0, negative 1. And on top, we replace, because we're looking for x's, we replace these x's with these answers. 6, 3, 0, 1, negative 1, 0, 1, 1, negative 1. Okay, and now I need to find each of these determinants. I could certainly pull out my calculator. I think I'm just going to expand along this row here because I have 0 times stuff plus 0 times stuff plus a negative 1 times, that's going to knock out these, 6, 1, 3, negative 1. Negative 6 minus 3 is negative 9. But remember your cofactor fabric, plus, minus, plus, minus, plus, minus, plus, minus, plus. We're over here, so I need to multiply by a positive. So I have this times a positive, so negative 9 times negative 1 is positive 9. So my x determinant is positive 9. Now what about my coefficient determinant? Well, I've got a 0 here, so I'm going to expand along this row. You can expand along, of course, any row or column, or you could even use your diagonals method. 3, 1, negative 1, 1, 1, plus 0 times stuff, plus a negative 1 times 1, 1, 2, negative 1. 1 minus a minus 1 is 2, plus 0, minus 1, negative 1 minus 2 is minus 3. Don't forget your cofactor fabric. We're expanding along this row, so this is going to be plus minus plus. This times a positive, this times a negative, this times a positive. And so we end up with 6 plus 3, which is 9. We get 9 over 9, or 1. Done. Why don't you find the y value? Find the y value. Y equals, using Cramer's rule. Okay, pause the video, give it a try. Welcome back. So I'm going to have the y determinant, which means I replace these y's with these answers. So I'm going to have 1, 2, 3, 6, 3, 0, 1, 1, negative 1. over, and we've already done this one down here. 1, 2, 3, 1, negative 1, 0, 1, 1, negative 1. I just did this and came up with 9. Okay, so on top, what do we have? Well, if I expand along this, well, let's expand along this just for variety. So I've got 6 times 2, 1, 3, negative 1. Let's try and get them a little closer. 2, 1, 3, negative 1. And then I have that 3, and that knocks out those, leaving me 1, 1, 3, negative 1. I did it again. 1, 1, 3, negative 1. And then finally 0 times some stuff. Okay, so this is negative 2 minus 3, which is negative 5. And here we have negative 1 minus 3, which is negative 4. And nothing over there. Now remember your cofactor fabric. Minus plus minus. So I have to multiply this by a negative. So I'm going to get positive 30. I have to multiply this by a positive, so that stays negative 4 times 3 is minus 12. And I have to multiply this by a negative, but it doesn't matter because it's 0. And so I end up with 18 over 9, or 2. And so we know that y equals 2 in this case. Y equals 2. And so we've got 1, 2, and all we need to do now is find z. Well, look, we already know x and y are 1 and 2, and so z must be 3. And so that's pretty straightforward. We only actually need to use Cramer's rule twice to solve that 3-variable system. And finding those determinants, even with minors and cofactors, is pretty fast. So Cramer's rule, very powerful, mid-1700s. Woo! Okay, so that's one thing that we can do with determinants. And of course you could find those determinants on your calculator, but they weren't that big a deal, so I decided to find them by hand. Now, what else can we do with determinants? Well, check it out. If I know that I have a triangle whose points are 4, 5 is this vertex, and 5, negative 2 is this vertex, and this vertex over here is at 0, 0. And I've got a triangle, and I want to find the area of this triangle. Well, it doesn't appear to be a right triangle, so I can't use 1/2 base times height. I could, I don't know an angle. I mean, I could find this side length and this side length and use 1/2 AB sine C if I knew that angle. I don't know that angle. I could use the distance formula to find the length of these sides, and then I could find this angle with law of cosines, and then I could do 1/2 AB sine C. Or I could use Heron's formula to find the area, provided I did the distance formula first here, and the distance formula first here, and the distance formula here, and then used Heron's formula and talk about the old school way. That's the old school way. That's the before the first millennium way to do this problem. And I'd like not to do the problem that way. I'd like to use the cool new, and by new I mean 16 and 1700s math of matrices to help us figure this out by using determinants. And here's what I know. I know that the formula for the area of a triangle is plus or minus 1/2 times the determinant of what? Well, it's the determinant of these ordered pairs, 4, 5, 0, 0, 5, negative 2. But wait a second. Remember, you can't find a determinant unless you have a square matrix. So I have to put in a column of numbers. Now, when I put in this column of numbers, they can't change the values. So if I put a 0 here, this that's not what I want to talk about. I need ones. I need a column of ones, because if I multiply things by 0, they become zeros, but if I multiply things by 1, they stay the same. So this is going to be my recipe for finding the area of a triangle. Now, this plus or minus here, it's not both. It's one or the other. If your determinant is positive, then you do times positive 1/2. If your determinant is negative, then you multiply by negative 1/2. We know area always has to be a positive number, but sometimes determinants are negative numbers, so we might have to multiply by a negative 1/2. Though, sometimes determinants are positive numbers. Area is always positive, so we'd want to multiply the determinant by positive 1/2. Okay, I will let you explore, and if anyone wants, who actually watches this video and is intellectually curious enough to explore, write me up the proof for why this works. I'm sure you can find it, maybe in your textbook, certainly online, but the proof for how does this, like I know the 1/2, base times height, somehow this is base times height. So look that up, write it up, email it to me, called area with determinants extra credit, and I'll give you that extra credit for showing me how to do it. Okay, so I need to find the determinant here. I'm going to expand along this row. You can find it any way you want because I know I've got a 0 and a 0. I just have to worry about 1 times 4, 5, 5, negative 2. I've got negative 8 minus 20 is negative 33. I'm sorry, negative 8 minus 25 is negative 33. Don't forget cofactors, plus, minus, minus. So I need to multiply that by a negative times the one that's out in front, and I get positive 33 as the determinant. And so we have 1/2 times 33, or 33 halves is our area. I think it's a pretty powerful tool, pretty fast for finding the area of a triangle when I only know the vertices. It certainly beats using distance formula, distance formula, distance formula, and then using Heron's formula to find the same value. So here's a triangle. Will you please find its area? Negative 3, or these are the vertices of a triangle, 2, 6, and 3, negative 5. Okay, so here you've got vertices of a triangle. Please find the area of that triangle. Remember, our formula is plus or minus, depending on whichever we need, a determinant. Okay, pause the video, find that area. Welcome back. Well, we know that the determinant is made up of these ordered pairs, these vertice points, but because we can only find the determinant on the square matrix, we need a column of 1s here. I'm going to do this on the calculator. Not that I can't do it by hand. I'm very comfortable doing it by hand, but I think that most of you should practice this, strangely enough, because, well, you're going to have a calculator on the ACT, and you might as well use it to find determinants. 3, negative 5, 1. Okay, so I quit back to the main screen. I go to Matrix, Math, Determinant, and I find the determinant of matrix A. And I get negative 56. Well, that's a negative number, so I have to multiply by negative 1/2 because I know that area is always positive, and I get an area of 28. Okay, the next thing I want to do with determinants is determine if 3 points are collinear. And I know you might say, well, first, what's collinear? Collinear means on the same line. You're probably saying, well, Mr. Kukla, I can see if 3 points are on the same line. It's not a big deal. Well, you know, when the points are when the points are, here we go, 3, -1, and 0, -3, and 12, 5, it may be a little harder for us to figure out if these are collinear or not. We could graph, but often our hand-drawn graphs are suspect for trying to answer questions like this. Okay, so I want to try and answer the question, how do I determine if these points are collinear? Well, let's go back to our area formula for a second. So I had these three vertices, and let's call them x sub 1, y sub 1, x sub 2, y sub 2, and x sub 3, y sub 3. And I knew I could find the area of this triangle by doing plus and minus 1/2, x sub 1, y sub 1, 1, x sub 2, y sub 2, 1, x sub 3, y sub 3, 1. Great. And I came up with some number that represents the area. Well, tell me what happens to the area if I move this point to here. What kind of a triangle do I now have? Well, I have a triangle whose area is 0. So the way we're going to determine if 3 points are collinear is just by determining the area of the triangle with those 3 points. And when we determine that the area of the triangle with those 3 points is 0, which means that the determinant is 0, because 0 times 1/2 will be 0, that's when I know that the 3 points are collinear. So let's do that. We've got plus and minus 1/2, 3, -1, 1, 0, -3, 1, 12, 5, 1. Okay. I practiced minors and cofactors. I practiced on the calculator. I'll use the diagonals method this time. 3, 0, 12, -1, -3, 5, 1, 1, 1, 3, 0, 12, -1, -3, 5. Okay, and I want these diagonals, the product of these, the sum of those products, which is -9 minus 12 plus 0, and that's -21. And then I want these there, there, and there. So I have -36 plus 15 plus 0. And so that's -21. And when I do one diagonal product minus the other diagonal product, I end up with 0. Since the determinant is equal to 0, I know the area is equal to 0, and therefore these 3 points are collinear. Okay. Will you determine if these 3 points are collinear? 2, -1/2, -4, 4, and 6, -3. Okay, determine if these points are collinear. Pause the video, give it a try. So welcome back. I know that the determinant made from 2, -1/2, 1, -4, 4, 1, 6, -3, 1. This determinant should be equal to 0 if these points are collinear. So let's try. I'm going to expand along this row. 2 times 4, 1, -3, 1, plus -1/2 times -4, 1, 6, 1, plus 1, times negative 4, 4, 6, negative 3. Okay, so I get 4 minus a minus 3, which is 7. And I get negative 1/2 times, this is negative 4 minus 6 is negative 10. And I have negative 12 minus 24 is negative 36. And don't forget the cofactor fabric, plus, minus, plus. So I have to multiply this by negative. So negative times negative is positive, but times negative 1/2. So I have 14 minus 5, and then minus 36, because a positive times this will still be negative. So I have 14 minus 41, or negative 27. So since that's not 0, I know that these points aren't collinear. Not collinear, because the determinant does not equal 0. All right, so that's using determinants to determine if points are collinear. The last thing I want to look at with you today is how to write the equation of the line using a determinant. I think this is really cool, right? So we're looking for y equals mx plus b, or even ax plus by equals c. All right, I want to write the equation of the line, and I know in order to write the equation of a line, I need two ordered pairs. So let's have two ordered pairs. Here we go. Sorry, I'm looking for something that I can't seem to find. Give me a second to see if I can find it. No, okay. So here we go. I want two ordered pairs. How about 2, 3, and 1, 5? Okay, so we're going to use the same approach where we know that these points are collinear. So I'm going to do that plus or minus 1/2 times the area thing, and that should equal 0. What are my three ordered pairs? Well, I have 2, 3, 1, 5, and I need another ordered pair. And that ordered pair is x, y. Don't forget the column of ones. And so now I want to expand along a row or column. This actually is much harder on people's brains if they try and do the diagonal method for finding this determinant. And I have to do this by hand. I can't use the calculator here. So let's expand along this row and see what we get. Plus and minus 1/2. And now we've got x times 3, 5, 1, 1, plus y times 2, 1, 1, 1, plus 1 times 2, 3, 1, 5. Okay, now before I start in over here, let's look over here. If I divide both sides by plus or minus 1/2, 0 divided by plus or minus 1/2 is still 0, and this becomes 1. So that goes away, and all I have to worry about is this. Okay, so this determinant is 3 minus 5, or negative 2x, plus 2 minus 1, plus 10 minus 3, 7 times 1 is 7. Don't forget the cofactor fabric, plus, minus, plus, minus, plus. So I have to multiply this by negative, which means this is negative, equals 0. Move the y over, y equals negative 2x plus 7, or instead of moving the y over, move the 7 over and get, or move these two over and get y, 2x plus y equals 7. I can get standard form or slope-intercept form simply by using this determinant of the area of a triangle with the third vertex being 0, 0, and knowing that those points are collinear, and I can write the equation of the line almost as fast, well, probably as fast as the Algebra 1 student can find the slope and the y-intercept. Maybe even faster, because some of them are really slow at it. All right, so for our last problem then, will you take these points, 2, 3, and 7, negative 2, and please write the equation of a line between those 2 points using this approach, okay? Welcome back. 2, 3, 7, negative 2. Remember, I need to expand along the bottom row. And remember, I'm going to multiply both sides, so really it's just determinant equals 0. So I have 0 equals x, 3, negative 2, 1, 1, plus y, 2, 7, 1, 1, plus 1, 2, 3, 7, negative 2. So I have 3 minus a minus 2, and then 2 minus 7 is negative 5, plus negative 4 minus 21 is negative 25 times 1. Don't forget the cofactor fabric, plus, minus, plus, minus. I have to multiply this by negative, and so I get 5x plus 5y minus 25. If I move this to the other side of the equal sign, I get 5x plus 5y equals 25, and that's in standard form, or x plus y equals 5. And I can write the equation of that line pretty darn quick. All right. Well, I hope that you found these matrix applications interesting. Good luck on your ACT, and I look forward to seeing you in the next video. Take care, everyone.